If you draw a complex network of lines on a piece of paper, you quickly run into a physical limitation. The lines have to cross. Sometimes a crossing is just the result of a messy drawing, and you can easily untangle it by shifting a few paths around. But other times, a shape is inherently intertwined. Proving the difference between a clumsy sketch and a shape that is strictly impossible to flatten requires rigorous mathematical proof. To solve this, we rely on two specific mathematical tools: planar graph embeddings and the winding number of continuous curves. Together, these concepts act as the critical bridge between intuitive geometry and the formalization of algebraic topology. The standard textbook for navigating this transition is James R. Munkres Topology. If we look at the structure of the text, this material sits entirely within Part 2, specifically Chapter 10, covering separation theorems in the plane. Up to this point, the book relies on pure point set topology, defining spaces through open and closed sets. But those basic definitions are not enough to easily prove whether two continuous lines are forced to intersect. To solve problems of spatial separation, we have to convert geometric shapes into countable invariants. That requires algebraic topology. Let's formalize our terms. A topological graph is a space constructed from a union of arcs, which meet only at distinct endpoints called vertices. Mathematically, this graph exists as an abstract set of relationships. Drawing it on a page is a completely separate action. That drawing process is an embedding, an injective continuous map from abstract graph space into the two-dimensional coordinate plane. Injective is the crucial constraint. No two distinct points can map to the exact same coordinate. If lines cross, injectivity fails. Planarity is therefore not a property of illustration. It is a strict question of whether a perfect, injective continuous mapping function exists. This diagram shows the complete graph on 4 vertices, K4. Drawn here, 2 internal edges intersect, but we can adjust the function. By stretching one edge around the outside, we eliminate the crossing. An injective mapping exists, making K4 planar. Consider a highly connected structure like K33. Mapping its first edges forms closed regions, acting as topological traps. Routing the final edge forces it to cross an existing line. That intersection is embedding failure, 2 abstract points mapping to a single coordinate. The two-dimensional plane lacks the necessary degrees of freedom. Highly connected graph structures oversaturate the available space, guaranteeing a violation of injectivity. To measure the rotation of a curve, we establish a geometric baseline. We place a distinct reference point, x0, strictly off the curve. Next, we draw a tracking vector connecting our reference point to point P resting directly on the curve. As point P traverses the entire loop, the vector sweeps around. The continuous accumulation of that vector's angle gives us our winding number. Because the curve is a closed loop, the tracking vector has to return to its starting position. Mathematically, the total angle change must be a strict multiple of 2 pi. In this setup, completing one full rotation yields a winding integer of exactly 1. This integer is a perfect algebraic invariant. Continuous deformations of the curve, stretching it or squishing it, cannot change this discrete numerical output. Watch the math change when the reference point is moved to the outside of the curve. As point P makes its journey, the tracking vector sweeps slightly upward to follow the top of the curve, but then it has to reverse direction to track the bottom. It fails to achieve full rotation. The positive angle is cancelled by the negative movement, leaving a net rotation of 0. The winding number remains completely constant across any connected component of the plane that does not intersect the curve. This discrete algebraic output, producing a 1 for points inside and a 0 for points outside, is the rigorous proof required to formalize the Jordan curve theorem. It confirms that a simple closed curve permanently separates the plane into distinct interior and exterior spaces. The highly connected graph and the simple closed curve represent 2 major problems of spatial separation. On the left, planarity is governed entirely by the existence of a continuous injective mapping. On the right, winding numbers convert continuous geometric paths into fixed algebraic integers. Point-set topology helps us define the spaces, but algebraic topology provides the rigorous counting tools necessary to prove geometric truths that intuition alone cannot resolve. Studying classical theorems in texts like Munkres requires a high level of rigor, forcing us to rebuild our understanding of geometry from the ground up. If you found this breakdown helpful, please like the video and subscribe. We will continue to explore the foundational texts of mathematics. Thanks for watching. Keep studying.